Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on January 15, 2026, just 2 days ago. It introduces a framework that improves accuracy on challenging benchmarks by nearly 9% over single-agent baselines, by injecting structured textual experience into multi-agent deliberation at inference time. The paper is titled, Collaborative Multi-Agent Test Time Reinforcement Learning for Reasoning. And as we'll see later, the implications for building robust reasoning systems without expensive training are really significant. Figure 1 provides a high-level overview of the MATTRL framework, using a medical diagnosis example. On the right side, the workflow proceeds through 3 stages. A recruiter first builds a custom team of specialists, who then engage in multi-turn discussions to reach a consensus. The core innovation, however, is detailed in the left panel, Test Time Experience Construction. Here, the system evaluates past dialogues to identify high-credit behaviors, distinguishing them from lower-quality outputs. It then distills these winning patterns into structured experiences, shown at the bottom left, which serve as textual guidelines to steer future collaborations. So, with the framework in place, Table 1 details the experimental results on the medicine benchmark. The columns track performance using metrics like hit at 1, which checks if the very first prediction is correct, and mean reciprocal rank, or MRR. Looking at the first 3 rows, standard methods like MD agent and rare agents hover between 0.32 and 0.35 for top 1 accuracy. However, in the bottom row, MATTRL clearly outperforms them, reaching a hit at 1 of 0.39 and an MRR of 0.51. This improvement suggests that the added test time experience effectively guides the team toward the right diagnosis. Alright, knowing which agent to credit for a success is crucial, and Table 4 compares 3 strategies for this: naive averaging, difference rewards, and Shapley approximations. The table tracks retrieval accuracy, and the second row highlights the winner, difference rewards. It achieves a hit at 1 of 0.40, effectively identifying the most useful experiences. In contrast, the third row shows that Shapley values perform worse on this strict metric, dropping to 0.35. This suggests that simply calculating the counterfactual impact of an agent, what happens if we remove them, is cleaner than averaging contributions across many potential coalitions. Well, applying those optimized mechanics to a different field, Table 2 presents the performance on HLE math problems. The baseline in the second column shows a single agent achieving an accuracy of 0.27. In the middle column, simply adding multi-agent deliberation improves the score to 0.33. But looking at the final column, MATTRL pushes the accuracy even higher to 0.36. This confirms that guiding agents with specific test time experiences yields better reasoning than just letting them debate on their own. So Figure 3 illustrates exactly what these injected experiences look like, using medical diagnosis as a case study. The top section lists general experiences, which act as high-level reasoning protocols applicable across many scenarios. For example, the second rule advises agents to anchor on key discriminators first, ensuring they prioritize decisive symptoms over vague matches. In contrast, the bottom section lists disease-specific experiences, which provide granular case-by-case guidance. A clear example here is the instruction for leukocoria, or white pupil, which explicitly tells the model to clarify the physical location of the symptom before assuming a specific disease subtype. Okay, having established how the agents think, Figure 2 asks how many should be in the room. It tracks accuracy as the team grows from 1 to 9 experts. The blue line at the bottom reveals that strict hit at 1 accuracy peaks at just 3 agents, likely because larger groups struggle to reach consensus. In contrast, the black line at the top shows hit at 10 rising sharply up to 5 agents. This implies that while larger teams are great for brainstorming broad possibilities, they add too much noise for precise decision-making. Wrapping up, 2 key takeaways stand out. First, injecting past experiences as text during inference enables rapid adaptation without the instability of training new weights. Second, this method yields significant gains in reasoning tasks, proving that guiding agent collaboration is often more effective than simply adding more compute. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.